My name is Kevin Thompson, and today I'm going to be talking about a collaboration I have with Ojas Parekh concerning an application of higher levels of the Lasserre hierarchy in quantum approximation algorithms. The first thing I need to describe is a quantum bit or a qubit. A classical bit I think we're all familiar with. It's just a variable. It can be plus or minus 1. A probabilistic bit is a random variable, which is just the toss of a weighted coin, which has plus or minus 1 values with different probabilities. A quantum bit corresponds to a complex vector. It itself isn't really a classical distribution, but you can use it to calculate probabilities of certain events happening. In the context of this talk, I want you to think about a generic quantum state, say on n qubits, as a exponentially large Hermitian PSD trace 1 matrix. There's a couple ways we could think about something like this. We could either describe it using its matrix elements, or we could choose a more convenient operator basis. And the classical analogy here is if I want to describe to you a distribution on n bits, I can do it either by listing the probabilities of each outcome, or I can give you increasingly non-local moments of the distribution. So these are actually equivalent representations of the same distribution, just that the second one might be more useful if your problem is local. So the quantum version of this involves the Pauli matrices. That's just these 4 matrices here, and their actual definitions aren't really that important. The important fact is that tensor product of n of these 2x2 matrices form a basis for the operator space corresponding to these matrices here, which are called density matrices. And there's a notation I want you to keep in mind that I use a lot. So if I write sigma I for sigma in this xyz, so sigma one of these xyz matrices, what I mean is Pauli sigma on qubit I. So I mean I want you to put the Pauli z on, say, the second qubit in the first example, and then I want you to replace all of the other gammas in the tensor product with identity. And z1, z3 is sort of the same thing. I'd have z1, z in the 1 position, z in the 3 position, and then everything else is the identity. N is always going to be the number of qubits. It'll be clear from context. The important thing about this basis is that it has the same property that the right-hand side does. The low-order moments give you kind of local information about your quantum state. So I can use these 3 entries, for instance, to compute a reduced density matrix, say, on the first qubit. And this is the density matrix you would get if, say, you threw away all of the qubits except the first one. There's another description of quantum states which is equivalent, which is essentially a redundant description in the Pauli operator basis. Given some density matrix rho, I want you to write down this 4 to the n by 4 to the n matrix, and I want you to put in each matrix element the corresponding basis element for the Pauli basis. So, for instance, I would have in the row corresponding to x1 and the column corresponding to x2, I would want to see trace of x1, x2 row in that entry. Similarly, I would also want to see this entry down here. So x1, x2 times the identity. These are the same Pauli matrix, so I'd want to see the same entry there. And it turns out this is actually equivalent. So if I have a matrix like this, which is 1s along the diagonal and it's PSD, I can define a density matrix, and the density matrix also defines a matrix like this. This matrix itself, the moment matrix, must also be PSD. This is like an easy calculation to check. The optimization problem we're going to be interested in is called quantum max cut in a couple places in the literature. In case you're unfamiliar with classical max cut, it's just the problem where I give you a graph and you try to find the best assignment of the vertices to plus or minus 1 values to maximize the total cut. So an edge is cut if the 2 endpoints have different values, say the blue edges in this example, and the edges uncut if they have the same value. So you can actually phrase this as an exponentially large semi-definite program in this kind of quantum notation. So you can define this Gij term If you look at the non-trivial part of the tensor product of all these things, you'll see that it has 1 if the edge is cut, and it has a 0 if the edge is uncut. So when you add up all of these local terms, you'll essentially get a giant diagonal matrix where diagonal elements correspond to assignments, and the value of the diagonal corresponds to the cut value. So when you maximize trace of row times diagonal matrix, you're going to get whichever diagonal entry is the greatest. So you're going to get the maximum cut value. To get the quantum version of this problem, I want you to just replace this ZZ term with this XXYYZZ term. And essentially, you just solve exactly the same problem. But now you're optimizing over generic row because the local term is no longer diagonal. This kind of local operator is sort of special. It's called the singlet, essentially a projector onto a local state on each edge. So in essence, the problem is sort of like asking, what's the density matrix which is closest to the singlet on each edge, where an edge is specified by the input graph? So why would we care about this problem? Well, it's interesting for a lot of physics reasons. Essentially, what you're trying to do is find the largest energy state of some physical system. And the reason people are interested in this is basically because it's a toy model for all kinds of phenomenon that are very interesting. So you can use it to describe kind of rudimentary superconductivity models and quantum phase transitions and quantum magnetism. There's a lot to cover with this model. Since the moment matrix picture is equivalent to the density matrix picture, you might guess that I can also phrase quantum max cut as an optimization problem on moments. And you'd be right. You can assume the graph is complete by potentially adding values to the edges and then setting some values to 0. And if you define this huge exponentially large cost matrix, you'll see that the optimization problem here on the left-hand side was going to give you exactly the same answer as this side. So these are just essentially kind of different representations of the same problem. This particular problem is QMA hard, which is sort of the quantum analog of NP. So we shouldn't expect to solve it, and the interesting direction is to try to find ways to approximate it. An approximation algorithm in this context is a classical algorithm that takes as input the description of your problem and outputs a classical description of a quantum state. So for us, the input is a graph and a set of weights, and it corresponds to this exponentially large matrix whose eigenvalue we're trying to find. The performance guarantee you normally have is that the output of the algorithm, so the objective that's obtained by the classical description of the quantum state, is at least some alpha fraction of the optimal objective, so the largest eigenvalue. Normally it runs in polynomial time, and the important thing is that the guarantee you get is independent of the instance. For the quantum case, though, it's sort of unlike the classical case in that the optimal kind of assignment is not clear. So quantum states are sort of murky, and it's not clear based on the Hamiltonian what kind of quantum state the classical computer should output. This is called the ansatz, and basically every algorithm comes with some kind of guess or form that the output takes. We're going to be thinking about two specific ansatz, the product state ansatz and singlets plus product states. So the product state ansatz is just sort of a collection of 1-qubit marginal distributions. You can think about this as independent coin flips. So it's a quantum state defined by individual density matrices on every qubit. There's also a singlet plus product states ansatz, and this is a collection of product states and also a collection of singlets. Since the objective is a singlet, this is like on this edge, if the objective had had a singlet term, we would obtain 1 on that term. So it's sort of like a more entangled thing which might do better on our particular objective. Quantum max cut is a relatively well-studied problem with all kinds of approximation algorithms known. So the early work listed here, these all make kind of strong assumptions on the topology of the graph. And they also apply to more general problems. But because they make these assumptions, they're invalid for the generic problem, which these new results cover. One thing to note is that all of the ansatz for these works, all except the previous state of the art by Anshu, Gassa, and Morenz, use the product state ansatz. This isn't great because quantum states are sort of generically non-product, especially the kinds of quantum states that we're looking for. So it's important to find quantum algorithms that round to better, more entangled states. This is the result we get. We beat the state of the art in the third decimal place, which isn't that exciting, but the real contribution, we believe, are some of the ideas we're presenting. So now we've set up the building blocks, and I've talked about previous work, we can start to actually describe what we do in the paper. So you could imagine trying to think how to approximate this exponentially large STP. You can write down sort of a cartoon of this matrix and wonder, how am I going to sort of approximate this exponentially large thing? Well, one idea is to approximate it by a polynomially large subset of the matrix. So you can optimize over this kind of submatrix and kind of not worry about the other elements. This is nice because the submatrix is still going to be PSD. You can assume all of the equality constraints that the overall moment matrix would satisfy. So, for instance, this entry would be equal to this entry. The catch is I'm optimizing over a submatrix. It's likely not embeddable into an overall global matrix. So that's why you get a relaxation on the optimal objective. I also wanted to find two submatrices of interest to us. So the first one is Lasserre 1, which is, I consider the submatrix consisting only of one local terms. And Lasserre 2 is, I consider the submatrix consisting of all one local and two local terms. From the previous slide, it's clear that higher levels are tighter relaxations on quantum states. By this I mean if you consider taking Lasserre 1 versus Lasserre 2, Lasserre 2 is a bigger submatrix which lets you capture more elements and more constraints, so you're getting a better approximation to your exponentially large moment matrix. For us, an important observation is that Lasserre 2 captures some monogamy of entanglement inequalities. In case you're unfamiliar, entanglement is sort of a quantum correlation between subsystems. And I want you to think of monogamy of entanglement as saying that you can enforce certain inconsistent quantum marginals. So I've drawn here sort of a classical picture and a quantum picture to compare. You can imagine wanting to enforce that along this edge, you see 1, 1, or 0, 0 with half probability, and trying to enforce that along this edge. But then it's impossible to enforce along this edge, seeing 0, 1, 1, 0 with half probability. And it's kind of the same thing over here. When I say trace row H23 is 1, then I'm demanding that along this edge, the quantum state looks like a singlet, and same thing along this edge and along this edge. Monogamy of entanglement says that this isn't really possible. And it, in fact, bounds kind of the sum of the closeness. So it bounds the sum of these three things away from 3. The main technical component is the star bound, which was proven in these works. It essentially bounds the closeness of a quantum state to a bunch of singlets where all of the singlets share a common point. So let's say I want to try to enforce that my quantum state is a singlet along here and a singlet along here, and then all of these edges, all up to Q many edges. Well, I can't possibly enforce this just by the definition of a quantum state. And monogamy of entanglement actually tells me sort of the sum of the closeness along each of these edges is bounded by this number, Q plus 1 over 2. For us, the star bound says that Lasserre 2 is also bounded in this way. So If I were to calculate my kind of value that I would get from the SDP along these edges and add them up, I would get exactly the upper bound that quantum states have. The important thing is that Lasserre 2 kind of crucially has this. So Lasserre 2 satisfies this monogamy of entanglement inequality, whereas Lasserre 1 is very loose on it. And there's also this Lasserre 1.5 thing, which I haven't really specified, but we use it in a previous work, and it gets something sort of in between the two. So what's the actual rounding algorithm that we're suggesting? We're employing singlets plus product state ansatz, and I want you to define this value. So for every edge, define this number. Then think about the value as how much the Lasserre 2 relaxation thinks that edge should be a singlet. So if the value is really close to 1, then Lasserre 2 is telling you, hey, I think in the optimal quantum state, this edge is a singlet, whereas if the value is low, it's saying it could be a product state. So the overall strategy of the algorithm is to choose edges to be singlets using guidance from Lasserre 2. So for the purposes of describing the algorithm, let's fix d to be some integer bigger than 1, and let's fix this alpha d function. So here's what we do. We solve Lasserre 2 to get M. So this is the polynomially large moment matrix, the submatrix. And you initialize this set of edges to be empty. This is going to be the set of large edges. These are going to be the edges that Lasserre 2 thinks could be singlets. And for each edge ij, calculate its value. If the value is above this threshold, defined by this alpha d thing, I want you to add that edge to the edge set. And then once you've done that for all the edges, find a maximum matching on the edges, and then consider two states. So one state, I want you to put singlets on the maximum matching and product states on the rest. And for the other state, I want you to just consider pure product state rounding and take whichever has better objective. So how does the analysis work? Well, we're going to do a standard thing, which was pioneered in this seminal work, which is you take the relaxation, you apply a rounding algorithm to it, and in the proof you have to bound the objective loss that the rounding algorithm incurs. So the thing you would think that maybe would be bad for the rounding algorithm would be, what if I have a bunch of edges that have large value and high degree? This would mean then that sort of putting singlets on the matching maybe doesn't really approximate the Hamiltonian. But fortunately for us, the point of the star bound is that it exactly implies that the edge set you get L has low degree. So this mysterious constant D that I was using is actually the max degree of L that the star bound implies. So if D is 1, you get you can just sort of take whatever edges are in L as your matching. If D is 2, you have kind of a union of cycles and lines, and if D is 3, you have a 3-regular graph. So the way to think about how it works is if most edges have large value, the maximum matching has good performance, whereas if most edges have small value, you don't really need entanglement to get a good objective function. You could ask, why not just set D equal to be 1, so that way you would guarantee that you can find the matching just by taking all the edges. And the reason for this is that if D is too small, product state rounding is actually bad. The reason for this is that the value of D you pick sort of chooses how you have to optimize, sort of like what regime the product state rounding needs to kick in. And if D is too small, the regime that you're using product state rounding on is sort of too big, and the analysis just sort of reduces to the previous product state rounding. So you're kind of using product state rounding too much if D is small. If D is large, it's pretty clear the matching is not a great approximation. There's a few additional proof techniques we use. So to prove the star bound, we sort of consider a star and we symmetrize over the vertices. And this brings the matrix to a standard form, and then we can use Schur complements to prove the star bound. We also use what's called sum of squares proofs. Essentially, the relaxation can also be interpreted as trying to constrain sums of squares of polynomials to be positive. As a result of this kind of interpretation, there are standard techniques for deriving bounds that your hierarchy or your STP will satisfy. So what are the implications? We've demonstrated that Lasserre 2 satisfies some monogamy of entanglement inequalities. This sort of says that sort of the low-order quasi-description of a quantum state can still look entangled, which I think is kind of cool. We've demonstrated an explicit gap between Lasserre 1 and Lasserre 2 in terms of expressing these inequalities. So we know for a fact on, say, the star graph that Lasserre 1 is quite bad, whereas on the star graph Lasserre 2 is exact. We've also described a approximation algorithm which produces an entangled output state, but follows sort of a standard meta-algorithm or recipe. So Gomez-Williamson, they solve the STP and they use the solution around to a feasible point. This has been an enormously successful branch of approximation algorithms, and this is sort of the standard formula that a lot of results use by showing that these quantum problems can also follow this sort of recipe. We potentially open the door to the rich background of classical techniques. There's a few open questions. There's no known hardness results for approximating these problems. We're also only really scratching the surface of Lasserre 2, we think. We think that Lasserre 2 is capable of producing a much better approximation factor. And some of these sub-questions are, what kind of graphs is Lasserre 2 exact on? That's something I'm actively working on. Are moments subject to other monogamy of entanglement inequalities that we can think of? And of course, can we get a better approximation factor? So more generally, I think an interesting question is, what kind of physical constraints are present in Lasserre K for K order 1? So this is like asking, what kind of quantum properties can we get from a polynomially large STP in this sort of very natural family of STPs? Another thing, which is the big open question, is singlets and product states are still locally entangled. They're still the tensor product of local things, even if they're not the tensor product of single qubit local things. Can we generate a rounding algorithm which produces sort of genuinely entangled things, like tensor network states, for instance? There's also this problem that we have a classical algorithm which produces a description of a quantum state. It would be extremely interesting if we could come up with a quantum algorithm which uses a quantum computer and produces a quantum state. Thank you.